So this video we're going to talk about and we're going to continue talking about inverse functions and inverse of functions, but specifically more we're going to talk about inverse functions. So hopefully we recognize now that inverse functions are going to be primarily what we're going to discuss throughout any of the math courses that we will deal with at usually the lower undergraduate level. So your calculus series, your trig series, but sometimes you'll see this in some advanced mathematical classes. But for right now, we're going to focus on inverse functions. So let's go ahead and look at an example. So let's just say that we have an example. Let's say we have f of x equal to a value of x plus 2. So this is a linear function, something very easy. So what I want to do is that I'm going to use this table just to plot some quick points. So if I let this top row be x, my second row would be f of x. So in this circumstance, I'm just going to go ahead and plug in some values for x. So here I would 0, 1, 2, 3, 4, 5, 6, 7, and 8. So when I plug these in, I'm going to have 0. I'm going to have 0, and then I will have, actually, let's make this fun. Let's make this let's make this 3x plus 2. So we'll say 3x plus 2. So then if I let x be 1, we'll have 3 times 1, which is 3, plus 2 will be 5. X be 2, we'll have 6 plus 2, which gives us a value of 8. 3, 9, 10, 11 for value of 3. For 4, we're going to have 14. And 5, we will have 17. 6, we're going to have 20. And then 7, we will have 23. And then if we plugged in 8, we would get a value of 26. So everything just increases there by a value of 3. So how would this relate to our inverse? So we know that since this is a linear function, we know that f inverse of x, let me do it in a different color, f inverse of x, we'll do this in blue, f inverse of x is also a function. So since f of x is linear, we know it is 1 to 1. Then we also know that f inverse of x is also a function. So be very conscientious about that. So now what I'm going to do is that I'm just going to go ahead and not at this point explain to you how to determine f inverse of x. I'm just going to tell you at this point that our inverse function, f inverse of x, of our function f of x is equal to x minus 2 all over 3. So now if I were to look at this being a separate function by itself, a lot of times you're going to see the notation of y and then f inverse of y. I'm just going to assume they're totally different. They're separate functions. However, there is a relationship between the two. Here, if I have my value x and my function f inverse of x, and I start plotting some points. So here, let's go ahead and I'm going to describe what happens here when I choose a value of 2. So when I let x be a value of 2, I want to have f inverse of 2. This will be 2 minus 2 all over 3, which gives me 0 over 3, which is a value of 0. So now I have a value of 0. OK, that's not so bad. Next, I'm going to pick a value of 5. So next, I'm going to pick a value of 5. And if I want to determine this, I'm just going to plug in a value of 5 everywhere we see an x. And we're going to have 5 minus 2 all over 3, which is 3 over 3. And that's a value of 1. That's interesting. And let's go ahead and continue. Sometimes I work left to right and up to down and top to bottom and left to right and right to left. So now I'm going to go ahead and choose another random value. And again, hopefully you're not seeing this is not so random anymore. I'm going to choose a value like 8. And that's a really poor 8. 5, 1. And this is a value of 8. There we go. 8. There we go. So we're going to find f inverse of 8. This is going to be equal to, this will be equal to, all I'm doing is plugging into my inverse function. And I know at this point I just told you what it is. And then we will learn exactly how to calculate and how to determine our inverse function. So we're going to get 8 minus 2, which is a value of 6 all over 3. And this is a value of 2. So notice what is happening. Look at this relationship is that here we had 0 and here we had a 2. And then our 2 became the 0. Our 2 became the x value. And then our 0 became the functional value. So the y value, in essence, the y value. Here we had a 1, here we had a 5, and look what happened. The range became the value of the domain, and the domain became the value of the range. That's pretty cool. Notice here, the range of our function became the domain of our inverse, and the domain of our function became the range in the inverse. And I bet you that we can also safely say that these values are going to be 11 and 3. The 11 and 3 will invert. This will become a 14 and 4. This will be 17 and 5. This will be 20 and 6. This will be 23 and 7. And this will be 26 and 8. So hopefully we can see that each value of our domain became the same value in our range, and vice versa for range and domain. So that is one of the unique properties that it's going to exist between all functions in the inverse. And here I just want to demonstrate to you how it worked between our function f of x equals to 3x plus 2 and its inverse function. Notice I said inverse function is equal to x minus 2 all over 3. So we're going to use this characteristic a lot to help us to determine the relationship between these functions, and we can guarantee that they are inverses. So now, since we've gone ahead and shown a slight example, an easy example about the relationships between domain and ranges, let's go ahead and talk about a way that we can determine a function and its inverse algebraically. So let's go ahead and talk about a method to determine a function and its inverse. So method to determine a function and its inverse function. So we're going to first say, let f of x exist as a function and f inverse of x be its inverse function. We at this point can guarantee two characteristics. So the first thing that we know is that we know f of f inverse of x is equal to a value of x. And this is going back to something called the composition. So hopefully we are all remembering our composition of functions. So if we don't have this right off the top of our head, remember this open circle that's sort of floating in the middle, and I should describe this a little bit better. So let me put this in the middle. There we go. Is equal to that composition. So remember, we define this. This is really us saying f of f inverse of x. And this is the first characteristic, and the second characteristic is going to be f inverse of f of x is also equal to a value of x. So these two characteristics that deal with the compositions will be equal to a value of x if the function and the second function are actually inverses of each other. So let's go ahead and look at an example. Let's go ahead and look at the example that we discussed before. So remember, we said that we had the example where we knew f of x was given to us, and that is equal to a value of 3x plus 2. And we were just told that there's another function. I'm just going to call this function g of x. And in the example, we said this was equal to x minus 2 all over 3. And in order for f and g to be inverses of each other, we know that f composed of g of x will have to equal to x, and g composed of f of x will have to equal to x as well. So if you compose two functions together and they are inverses, they will equal to a value of x. So let's go ahead and try that out and see how this goes. So let's look at this first characteristic here. So if I examine f composed of g of x, this will be equal to f of, and I'm going to do g of x in a different color. I'll do it in green. So we're going to label this value a bright green so we can't miss it. F of g of x. So everywhere in f we see an x, we're going to plug in g of x, which is equal to that x minus 2 all over 3. So this will equal to 3 times x minus 2 all over 3. And then we still have to add 2 at the end. Hopefully we recognize after we simplify that our 3's will cancel, and we are just going to be left with x minus 2 plus 2, then the negative 2 and the plus 2 cancel, and we're left with a value of x. So our first characteristic will hold true in this example. And let's go ahead and look at this second one. Let's go ahead and prove this second one. So we also have to show that g composed of f of x also equals to a value of x. So this is going to be bright green g, and here we'll say of f of x. And this will also have to be equal to a value of x. So everywhere in G, we see an x. We're going to have to plug in 3x plus 2. So this will be, I'm going to plug this in using parentheses, 3x plus 2, still minus 2 from up here, all divided by a value of 3. And this is going to be all divided by a value of 3 because we divide x minus 2 all over 3, so we're going to have to divide everything divided by 3, divide everything in the numerator divided by 3. Hopefully we recognize that in the numerator, those parentheses really don't have any mathematical importance. So this will just be 3x plus 2 minus 2 all over 3. We should see that the 2's and the negative 2 cancel, and we're left with a value of 3x all over 3. And these 3's cancel, and we're just left with a value of x. So notice now that our second characteristic also equal to x as well, and we can therefore guarantee that f of x and g of x are inverse functions. So we can say that f of x and g of x are in fact inverses of each other or inverse functions. So that is a very safe conclusion. So you can use the composition of the two to determine whether or not they are in fact inverses.